This is a continuation of Lecture Essay 46. In the previous lecture, we looked into how the matrix displacement method can be used to analyze indeterminate beams subjected to joint loads only. Here, I am going to expound further on how the formulation can be used to analyze beams subjected to member loads as well as joint loads. The basic idea behind this revised formulation is rather straightforward. When analyzing member loads, we simply replace them with their equivalent joint loads, then proceed with the analysis as was described in the previous lecture. Consider an indeterminate beam. It consists of two beam segments. The left segment is subjected to a concentrated load, while the right segment carries a distributed load. For segment AB, if the concentrated load was not present, we would have expressed the relationship between member end forces and displacements as described below. Here, F1 is the shear force and F2 the bending moment at the left end of the segment. F3 is the shear force, and F4 the bending moment at the right end of the segment. Further, D1 is the vertical displacement and D2 the rotation at the left end of the segment. D3 is the vertical displacement and D4 the rotation at the right end of the segment. However, when a load is placed on the member, we need to expand the formulation by adding a force vector to the right-hand side of the system of equations. The elements of this vector are the fixed end forces due to the applied load. To see why that is the case, please review Lecture Essay 45. In the aforementioned lecture, we showed how to arrive at this system of equations using the slope deflection formulation. If we have a concentrated load P placed at the midpoint of a beam segment with length L, then the force vector becomes But where do these values come from? They are the fixed end shear forces and bending moments experienced due to load P. That is, if we assume the ends of the segment are fixed, then the reaction forces become These are the forces used to populate this vector. Note that this bending moment is shown with a negative sign, since, according to our sign convention, clockwise direction is considered negative. We now need to transfer these fixed end forces to the adjacent joints and treat them as equivalent joint loads for P. To do this, we simply reverse the direction of each force and place it at its nearest joint, like this. In the case of our beam segment, since P equals 40 newtons and L equals 6 meters, we get Let's now rewrite the member equations using these values. We are going to follow the same procedure for finding the equivalent joint loads for the distributed load in segment BC. Here is the system of equations for the segment. Therefore, the equivalent joint loads for the uniformly distributed load of 3 kilonewtons per meter can be written as Here is what we get at joint B, and here are the forces at joint C. In addition, the member equations can be written like this. To summarize, the beam is subjected to two sets of equivalent joint loads. Therefore, the cumulative joint loads become Now that we have transformed the member loads to joint loads, we can proceed with the analysis of the beam as was described in Lecture SA 46. The beam has 3 degrees of freedom, which are rotations at A, B, and C. Let's label them as D1, D2, and D3. These are the unknowns we wish to determine. Since there are 3 unknown displacements, we need to formulate and solve 3 equations. In matrix form, the equations are written as This is known as the system stiffness matrix. F1, F2, and F3 are the joint loads in directions 1, 2, and 3 respectively. We just computed their values. F1 is negative 30 kilonewton meters. F2 is 26 kilonewton meters, and F3 is 4 kilonewton meters. Note that since the joints of the beam are not going to displace vertically, the vertical joint loads do not play a part in our formulation. As for the coefficients of the system stiffness matrix, they can be easily computed using the elements of the member stiffness matrices as follows. K11 of the system equals K22 of member AB. Thus, it equals 2EI over 3. K12 equals K24 of AB, or EI over 3. K13 equals 0. K22 equals K44 of AB plus K22 of BC, or 2EI over 3 plus EI, or 5EI over 3. K23 equals K24 of BC, or EI over 2. And K33 equals K44 of BC, or EI. Therefore, the upper part of the matrix looks like this. Since stiffness matrices are always symmetrical, we can easily generate the lower part by transposing the upper part as follows. Our system of equations then becomes Using the Gaussian elimination method, we can solve this linear system of equations. The elements of the unknown vector and the unknown joint rotations become Now, all we have to do is to substitute these values in the member equations to get the member end forces. First, let's write the member end displacement vectors. For segment AB, we know the vertical displacements are 0. The rotation at the left end of the segment equals d1, and the right end of the segment rotates by d2. Thus, the displacement vector can be written like this. Substituting the vector here gives us these member-end forces. Knowing the member-end forces, we can draw the segment's free body diagram. For segment BC, the displacement vector is Substituting it here, we get these member-end forces. Here is the free body diagram for the segment. With the two free body diagrams, we can easily determine the beam's support reactions as follows. See if you can analyze the following beams using the matrix displacement method.